In this video, we are going to look at some math topics that will be important to us throughout these videos. Also, in the previous video, I realized I forgot to explain what this notation right here means. So what this is telling us is that we're taking a partial derivative of the pressure with respect to temperature, and we are holding the volume and the amount of stuff constant. I did run this by some more mathematically inclined colleagues of mine, and they say this is somewhat of an abuse of notation, but I did check some of these on my own and they do actually work out. So even though what we're talking about here might not make the math people happy, it does seem to work for the purposes of thermodynamics. So anyway, what we have going on here is the partial derivatives obey some of the same algebraic rules as fractions. Again, this is the thing that my math colleagues were not very happy about, but it does seem to work out, so we are just going to run with it. So for instance, we can have this. So we're taking the partial of the pressure, which is a function of volume, amount of stuff, and temperature with respect to temperature. And so we use this notation for it right here, where we're putting the variables that are held constant as subscripts out here. This is another thing that my math friends didn't seem to like, because when you take a partial derivative of something, then it's just assumed that the other variables that you are not taking the derivative with respect to are being held constant. And so this ends up being somewhat redundant, but again, it seems very common in the thermodynamics literature, so we're just going to run with it. So when we say that these obey the same algebraic rules as fractions, if we then wanted to get the reciprocal of this, we would just take the reciprocal of everything. So now taking the reciprocal instead of the partial derivative with respect to temperature is the partial derivative of temperature with respect to pressure here. And so then this also gets flipped upside down. So instead of nr over v, it becomes v over nr. And also the partial derivatives can multiply through just like fractions. Again, this is that thing that the math people hate, but it seems to work for this, so we're going to run with it. So for example, if we have a, which is some function of two variables, b and c, where it can be written in function form like this. So a as a function of b and c, but then b and c are both functions of d and e like this. So what we want to do is take the partial derivative of a with respect to b here. And so what we get is this. So we're holding c constant, and we're taking the partial of a with respect to b. We use what's called the chain rule, and we end up getting this. When we look at pressure, volume, and temperature, we can use the above here to come up with the cyclic rule. So for a given amount of gas, pressure depends on volume and temperature. For volume, it depends on pressure and temperature. And for temperature, it depends on pressure and volume. For any general state variable, so like this f here, that's a function of volume, pressure, and temperature, its derivative with respect to temperature at constant pressure is this. So this is our partial of this function here that is dependent on volume, pressure, and temperature with respect to what should be temperature here. So I'll just change that to temperature. So we're just getting the partial of this function f here with respect to temperature, holding the pressure constant. And that gives us this right here using the chain rule. But we can see that the partial of temperature with respect to temperature will just be equal to 1. So this thing right here in the darker brown just becomes 1. So we end up with this. But if f is just the pressure, then we get this. So we have the partial of f with respect to temperature, but we are saying that this is the partial of pressure with respect to temperature, but we're holding pressure constant, so this will be equal to 0 because the pressure is not changing. So this gives us this right here. We can then rearrange this by subtracting off this right here from both sides, so we end up with this. Then we can divide both sides by the stuff on the right hand side here, and what we end up with is this. So we have this partial of pressure with respect to temperature times this partial of volume with respect to pressure times this partial of temperature with respect to volume, and this all equals -1. Again, we can think of this like fractions in algebra, where we see this pressure right here will cancel with this pressure, this volume with this volume, this temperature with this temperature. And so when we multiply all these together, we get -1. And this is called the cyclic rule for partial derivatives, or also the triple product rule. So each term involves the pressure, volume, and temperature, and so is independent of the equation of state. Knowing any two derivatives, you can use this to determine the third, because we know that if we have, say, two of these, then we know that the third has to be what it is, because when we multiply all three of them together, it has to be equal to 1. And this is regardless of the equation of state of the gaseous system. This is instead sometimes written like this, where we can see that now we have this partial of pressure with respect to temperature is equal to this divided by this. So this is just the inverse of this green one up here, and then we just divide both sides by this light brown one here. And so that gives us this right here, and so that's just the same as writing it like this, which is the way we had it written right up here. And we can check that this actually works. So these are both partials of volume with respect to temperature and then pressure, and so we can see that because volume is equal to nRT over P, if we want to put those in right here for the volume, then what we end up with is nR over P divided by negative nRT over P squared, and so that gives us P over T for this derivative right here. But we can see that using that pressure is equal to nRT over V, if we take the partial of P with respect to temperature, so then substituting this in for the pressure, we end up with nR over V. But we can see that if we take our PV equals nRT, divide through by V and by T, we end up with this right here, which means that having this come out be equal to nR over V is the same as having it come out being equal to P over T. And so we can see that the partial of pressure with respect to temperature at constant volume is P over T. If we want to look at another example of this, so let's say for instance we have this expression right here, and we want to find the expression for the partial of volume with respect to pressure at constant temperature and amount of stuff here. There is an expression involving volume, pressure, and temperature on the right-hand side of this equation, but it is the reciprocal form. So instead of this purple version right here, we have the reciprocal form right there up in this equation. That means we can take the reciprocal of the entire expression, so we end up with this. So this is our reciprocal here with respect to this partial of pressure with respect to volume, and so that just ends up being our purple one right here. Then to solve for this purple one here, which is the partial of volume with respect to pressure, we can bring this over to the other side so that we end up with this right here. So now we have this by itself on one side of the equal sign. And so we found the expression that gets us what we want. If we want to evaluate this to see if it actually works, so remember the temperature is equal to the PV over nR, and the volume is equal to nRT over P, and so we will put those in for the temperature and volume, which is what we are taking the partial of up here. So we put this PV over nR in right there, and this nRT over P right there. We evaluate these and we end up with negative V over P. Since the volume is equal to nRT over P, we can substitute that in for the V right here. So that's what we're doing right here. And so we see that we end up with this P ending up in the denominator. So we get the P squared. So we get the nRT over P squared. And that's exactly what we would expect if we just evaluated this partial derivative by itself. So we put the V in here. We substitute this in for V, and we end up with the negative nRT over P squared. And so we can see that this cyclic rule does actually work, even if it is an abuse of notation and all those other things that my math colleagues told me about. It still ends up working, and so that's why people keep using it. And so finally, we want to talk about a couple of important derivatives here. So we can have what's called the expansion coefficient of a gas, which is denoted alpha. This is the change in volume as the temperature is varied at constant pressure. And so we just define it like this. So the alpha is equal to the 1 over volume times the partial of volume with respect to temperature at constant pressure. If we evaluated this for an ideal gas, what we would get is R over PV right here. Then we also have what's called the isothermal compressibility of a gas, which is denoted kappa. This is the change in volume as the pressure changes at a constant temperature. And so this is the negative 1 over V, and then this is times the partial of volume with respect to pressure at some constant temperature. And we see because the volume will go down as pressure increases, then this is negative, and so having this negative sign right here will turn it positive. And so the negative sign makes the kappa positive. For an ideal gas, this is what we would get for kappa right here. So this 1 over V factor that we're putting in here on both of these derivatives, this makes the quantities intensive. So that means independent of amount. So recall that intensive properties like temperature and density are independent of the amount of material, while extensive properties like mass and volume are dependent on the amount of material. Having this 1 over V here makes the alpha and kappa independent of the amount of material, because if you add more material, that's going to increase the volume, so you're just dividing by a bigger number, and so that's going to make it independent of the amount of material. So what we see up here is that this alpha and this kappa are both going to be derivatives of volume. So one is the derivative of volume with respect to T, the other is the derivative of volume with respect to P. And so we can use the cyclic rule to find that the derivative of pressure with respect to T at constant volume is actually equal to alpha over kappa. So this is done using this. So we have our derivative of temperature with respect to pressure right here. And then these are the two partials we used in the derivatives up above for alpha and kappa. So we see that we're just dividing one by the other. We can multiply by 1 over v divided by 1 over v, because remember, anything divided by itself is just 1. So we're just multiplying by 1 here. But now we end up with this 1 over v times this partial of v with respect to p divided by this negative 1 over v. So I've just taken this negative and moved it down here so that we end up with the same thing as we had right here. And so we see that this is the negative 1 over v times the partial of v with respect to T at constant pressure. So this is just alpha over kappa right here. So we again see that this cyclic rule works even if it is an ugly abomination that the mathematicians accuse it of being. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.